Alright, hello everyone. So in this video we're going to try to go over some of the design practices that we'll use for making the cases for our electronics for the Baja buggy. And just a little bit of a disclaimer, this isn't a process that we see in industry. This is more of a hobbyist style approach, but as with most things we're doing with Baja, because it's a prototype, working prototype, we're going to do things in a manner that gives us a little bit more freedom of ease of manufacturing and practices like that. So the case design that we're going to go over today would never apply for a mass production environment, because you'd use some manufacturing process like injection molding, and we're going to be 3D printing everything. Okay, so the first thing is we need to make sure that we have a step file of our 3D board layout. So we can see that here, that we have a 3D model of the PCB, and this is the fuel gauge specifically. So I'm using SolidWorks. You're welcome to use whatever design CAD software you want. Additionally, I'm not really going to talk a ton about the actual drawing of these parts. I more just want to touch on how we can find components to use, what components we regularly use, how to make things waterproof, and protection against stray EMF. So let's go ahead and jump into this. So pull up the case that I have put together. And we're going to go ahead and roll back the feature bar all the way to the beginning. Okay, so we have the PCB here, and the first thing, I'm just going to quickly run through all of the different steps that I did to make this case so you can kind of see. So it all starts out super blocky. We had some holes for the PCB, and this is a good time to note, more times than not, we'll use M3 screws for holding the PCB down to the case. And the reason for that is they work out to be a good size, to not take up too much room. They're super available. And additionally, we'll talk about it more here in a minute, but we have access to heat set inserts. Basically these holes here, we take a heat set insert, heat it up with a soldering iron, and then press it into the hole. They're made of brass, and that gives us nice metal machine threads so that we're not wearing out the threads. If we just screwed these machine screws into the plastic, the threads would wear out quickly. Okay, and we'll go over, I'll throw some standard sizes up for that. And all the CAD resources will be in the teams. Okay, so now we go ahead and we're just moving along with more case stuff, blocking out the case. So we have some halves here. Introduce the lid. I'm going to go ahead, I think these next ones, so these are adding the holes for the connectors. Yep. So we're going to be using the M12 style connectors that we talked about. They're nice and waterproof and are quite cost effective. So we're going to plan on using those, and a model of those will also be available. So these are going to be the holes for those two connectors. That's what this board, every board we design will have a CAN connector, which will be one of our 4-pin connectors. So it'll have a ground, a 12-volt supply, and then our CAN high and CAN low. And then additionally for this board, we have an 8-pin M12 connector that we're using for all of the Hall effect sensors. Okay, so if we keep moving, we're going to add some bosses here. These will be what the case uses to mount to the frame. So our screws will go through here. Move along, so now we're adding holes in the top of here. Again, I like to use M3s. They usually fit well on these small cases. None of this stuff is set in stone, so you're welcome to choose whatever you want. Just know that for the heat set inserts, we can only get metric sizes cost effectively. All of the standard size heat set inserts are quite pricey. So we use metric for those. Okay. So yeah, this is the rough outline of the case, and then in the next part we just add a bunch of fillets to make it look nice. Okay, so that's where we get the majority of the body done. And then if we went through here, just adding chamfers to all the holes. And in this next part, I'm going to hide the lid real quick. Is it going to let me do that? Okay. Okay, so now this is a good time to talk about waterproofing. In this next step, we're going to add a O-ring groove around this whole thing. And the O-ring that we use, we buy cord stock, which is just a big long string of the O-ring material, and it's 1/16 in diameter. And we can use super glue to glue those together, so that's actually super common practice of making custom O-rings, as you just buy the cord stock and then you glue them together. Okay, so that way we don't have to worry about the length of this groove here. We can make it whatever we want, and then we'll glue together custom seals. And the 16th inch material I found to work best with the discrepancy in the flatness of these parts. The next size down O-ring is really too small to make stuff waterproof. It's very difficult. So the 16th inch stuff has proven to work fairly well thus far. So that's this feature here, and let's take a look at the dimensions here, because you can use these same ones. So this is a mid-plane thin feature cut, which if you're not familiar with, this blue line in the middle here is the sketch that I drew on the face here, and then the mid-plane thin feature means that it's just going to cut either side of this. So we have 1.9 millimeters here. So from this yellow line to this yellow line, the whole width of the groove is 1.9 millimeters. And then the depth of the groove is going to be 1.8. And I've tried this quite a few times, and this seems to work out fairly well. So feel free to use the same dimensions. There's plenty of resources and machinist guides as to making O-ring grooves and dimensioning them. But like I said, the 16th inch cord stock that we get works well with these grooves. Okay, so that lays in there, and then our lid is nice and flat on the bottom, so it'll seal. So we'll go through and add a few more things. So yep, we add the holes. So these are going to be heat set inserts again too. So we'll heat them up, drive them in here, and then we have brass threads to screw into. And then the last thing we have here, oops. Okay, let me back up actually. Okay, so the last thing we have here, well, second to last, these cases that we make, because we're 3D printing them, we don't have any EMF shielding, which typically on most widely manufactured vehicle electronics, you see a lot of their electronics being in some kind of metal case. And the reason for that is, if you're not familiar, we can have stray cosmic waves that, or just random EMF that it's capable of changing values inside registers on these sensitive electronics. So if you have, the whole buggy itself has a lot of EMF noise. So it's important to shield these. So we're going to make Faraday cages out of these, because in a typical metal case that's fully surrounded, it's a Faraday cage anyways. And they do make conductive filament that you can use, but it's fairly expensive, so we're going to go a different route. And the route that we're going to go is using double-sided conductive tape. so it's conductive through its adhesive as well as on top of it. So what we're going to do, and the reason that the inside of this case is still very square and blocky, is because we're going to take that tape and line the whole inside of the case with it. So the lid will get the whole bottom side coated of it, and then we also will coat the entire inside of this case with that conductive tape, and that will make a metal barrier around it. And the specific tape that we're using, I mean, it's made for this purpose. There's a couple brand names called EMF tape. So with that, we'll see here in a second. Actually, let me go ahead and I'm going to come back to this little feature down here once I can turn the screw back on. So the next thing is the metal sleeves here. So these little tubes here are going to be metal that are pressed into the holes here in the case. And the reason for that is that when our screw goes through here to clamp down, we want to be able to tighten it and not worry about splitting the plastic. There's quite a bit of clamping force on even small screws, like these are going to use 1024s. And the clamping force is definitely high enough that we can easily split the case. So that's one reason we want to use these. The other reason is because we're going to actually use these to ground the whole chassis. So we are going to have grounded chassis for all of these cases. And that's what we'll see here in a second, but this hole is for a screw. So let me go ahead and turn that on now. So I'm going to exit out of this part. Okay. Yeah. Okay, so like I said, the whole inside of the case is going to be coated in conductive tape. And then this screw down here, we can see the tape can easily be stuck over top of this, and this is a stainless screw, so it'll be plenty conductive on the surface. And we can just stick the tape right over top of this, and this screw presses right up against this metal sleeve. So we'll have a nice connection through the case to ground, so that we have a grounded chassis. And the other thing is we'll make sure that we silicone the threads around the screw. It'll probably be watertight anyways, but we'll silicone it too, so that this whole thing is still plenty waterproof. Okay, so I need to go back and turn on the lid here. Okay, there we go. Okay, so and we also have these M12 connectors here. So the next thing is I want to talk about fasteners a little bit. So we already talked about some of the threaded inserts. So our threaded inserts, like I said, were limited to metric sizes. But for the remainder of our mechanical connections, anything that we're not forced to use metric, it's going to be beneficial for us to use standard fasteners. And specifically just our mounting fasteners is what I'm talking about here. And the reason for that is we have lots of standard size fasteners on hand, and anything that as far as mounting, like we can take this case off and then have our own tools to work on it, but ideally all of our components that mount to the buggy are going to be standard sizes so that we don't have to fumble between standard and metric fasteners when we're working on it. So as far as the fasteners go, let's look at this here. So I'm going to turn on a couple of these fasteners. Okay. Turn on a couple more. Okay, so these are 1024 screws. I didn't really get fancy with picking out anything here. They just looked like a decent size to hold this thing. Didn't look too big or too small. And as far as fasteners go, we want to pick fasteners off McMaster-Carr. because the school has an account with them. So we can easily have Joey order them for us. And then additionally, the neat thing about McMaster is that they have models of all of their fasteners, so we don't have to worry about drawing any of these, and then we have nice models on them. So first I'm going to show you, if you go to their website, we can pull up fasteners here. So for example, we'll pick out one of these M3 screws. So we want to go metric, M3, and then something that we can do, and SolidWorks specifically, I can't attest to how to do it in other CAD softwares. It's definitely a feature in all of them, but we can go to evaluate here, measure, and then we can measure the depth of the hole here. That's in inches, so we'll go over to metric. Okay, so we have a 10 millimeter hole, so we need a 10 millimeter, well, we need less than a 10 millimeter fastener. So our length here, we're going to go to 8, and we want to use, for the most part, we like using the black oxide fasteners, and the reason for that is that they're cheap and they don't rust. So now that we have this, we know that we'd like this fastener, so we can go to details, and it has a sketch of the dimensions here. So we can use this for the countersink, the counter bore hole size, as well as all the depths. Excuse me. But like I said, the cool part is now we can go through and we can download all of these different 3D and 2D drawings. So for SolidWorks, we can just download it. And then once we have that downloaded, we can just drop it in, and then it contains our part number and everything. So very convenient. Okay, so we did the same thing with this. Other thing I wanted to show too is that if you are using SolidWorks, there's actually a McMaster add-in. So you can see I have that installed over here, so we don't even have to have the web browser. And you can see that the add-in actually keeps track of all the parts that we're using already and all the quantities, which is super nice. Because at the end of this, just like our bill of materials for the PCB design, we're also going to want to have a bill of materials to add to when it's time to order them, and then also just to have a parts list or a fasteners master list. Okay, and then we can go to find here just like we did before, and it brings up our nice search, and then we can add everything in from there. Okay. Okay, so that being said, let's see what's next. Okay, let's talk about mounting brackets real quick. Okay, so the mounting bracket I have here, we're going to plasma cut. So we have a plasma cutter down in Joey's shop, and we like using it for all of these sheet metal brackets because it's super quick. So when we design these brackets, the most important thing to keep in mind is that the surfaces left from the plasma cutter are quite rough. Not in the sense that they're jagged or anything. It's just that when the arc actually gouges through the metal, it frequently leaves little like boogers and stuff that we have to chip off. So it's not a super clean cut. And the important thing to keep in mind there is that the hole sizes need to be quite a bit oversized. We usually go 30 to 50 thousandths over what it actually needs to be. And the reason for that is just so that we have plenty of clearance so that these fasteners can all actually make it through. Because when the edges of these parts are plasma cut, it actually hardens them, so it's very difficult for us to drill the holes out. So if we're making a bracket, for example, if these holes needed to be precise, then we just wouldn't include them in the DXF file that we use for plasma cutting at all, because we would just plasma cut the outside of this part and then throw it on the mill and drill the holes later. If the holes had to be precise. For stuff like this, well, you'll see in a second here why it doesn't really matter. But if you want to plasma cut holes, make sure they're 30 to 50 thousandths oversize. Yeah. So 30 thousandths on small fasteners like 1/4 inch and less, and 50 thousandths on 1/4 inch and above. Okay. So the other thing is we have some holes here in the center. And the reason for that is because this mounting bracket is likely going to get welded onto a tube. Most of the mounting brackets we made are getting mounted to tubes, not flat sections. So the beauty of these holes will be that we can just set the bracket right tangent to the tube, and then we can weld through the holes and use those as spot welds, which will hold it on there, and then we can grind it flat. Okay. And then finally, the last thing we have here are some nuts for these screws. Okay, and the plan with these nuts is that we will use them to we'll actually weld them to this plate. So that's why I was saying the hole sizes can be quite large. So we'll go ahead and we'll attach these screws in here to use as clamps, and then we'll actually tack weld these nuts on here, and then those will be part of the bracket. And the reason we like doing that is because it just makes it a lot easier when you go to actually mount these brackets. You could just screw in the 4 screws and not have to worry about using a wrench or anything or dropping these nuts. So for small fasteners like this saves a lot of time and makes assembly and disassembly a lot easier. So yeah, outside of this, the only thing that I would like for us to do is to make sure that we have a nice parts list, just in like our individual module documentation. I'd like to have a nice parts list of all the fasteners that we're using, all of the connectors that we're using, as well as any mounting brackets that we're using. Have DXF files for that we can send over to have plasma cut. Yeah, and then the last thing, I guess, to keep in mind, it's something very easy to forget. We do a section view here. So clearance in general is just something important to keep in mind. So all of our components that are through hole, I think for the most part it'll just be our connectors. But anything that's through hole, we need to make sure that we have clearance on the bottom for all of those leads to stick through. And then additionally on your PCBs, make sure that you have a ground ring around your mounting holes, so that we can actually ground them to the case itself. And as far as clearance goes for the through holes, since we're going to use M3 screws, 3.2 millimeters usually works out well for clearance. Additionally, a big thing to keep in mind is the clearance for all of the wires here. I mean, for example, this connector is going to have 8 wires coming off of it, so we have to make sure that we have sufficient room. So if we look here from the board to our connector here, we have about 11 millimeters, so that's probably on the close side, but we can definitely jam those wires in there. But just keep in mind that the wires will quickly stack up. And the reason for that is because we need to make sure that when we take this top case off, we have enough wire to where we can actually like flip it over and unplug the connectors. Because when we go to put the top half on, we still have to have enough room to be able to plug the connectors back in. So this module is about 3.5 inches long, I believe, about 3 wide. So that means we'll have to flip the whole thing over. So we'll need like probably a good 3 inches worth of wire on there. So that has to all fit in here. So we should have sufficient space in here, but just something to keep in mind. It's never fun when you go to put a case together and you have to really jam all the wires in. It just doesn't make for a great design. Yeah. So all in all, that's the general idea of what we're doing here. Like I said, on Teams, there will be all of the resources for all of these parts, the heat set inserts, the connector drawings, the O-rings, all that good stuff.